Okay, thank you for the invitation to present to you my views about certain materials and processes, and have gone through in my lifetime in a lot of these situations, and I think you can gain some of my knowledge that I got through this procedure. So what do I do? Okay, my co-authors are my youngest son, who is, because of the coronavirus, he's in the hotel writing an exam in Canada. Well, he was in Czechia working for Amazon, and now he has to pay the price for all these things. So, presently I am I'm still doing research, although I'm supposed to be an emeritus professor and emeritus dean of engineering. Still I do work, and the second co-author, the second, Georgiura, is a former student of mine who runs the program of engineering at Dalhousie University. So what do we do again? Okay. Well, since this would be my 50th year that I live outside of the country, although I was born here, I was educated here, I got my first degree at the Technical University of Nova Scotia, did my military services, but because I had dictatorship at the time, I was not allowed to work here, so I moved to Canada. And since I moved to Canada, I went to the States, and then I went to Japan, to China, and all these things. So then, to me, it looked like a journey, and as probably you know, that during the ancient times, there was a Trojan War between two big states, and in one of these things was the person from the Ithaca, which is an island on the Ionian Sea, who contributed the Malaya to defeat the West. It was always East-West. And then he challenges the gods, and the gods try to delay his return home. So it is actually, I saw my life as a return home, and that's why here is when I went to Japan. Japanese wanted me to explain to them what I have done. So over here, this is my name in Japanese, and I call it the Kipouros Odyssey, how I moved from one place to another. So at the University of Toronto and MIT later, I got into the molten salts practice. Don't forget that this conference is supposed to be how mathematics help the processes. But if you ask a chemist to hire a mathematician, they will kill him out. If you ask the mathematician, will be able to solve all the problems, not understanding the importance of the properties of materials and processes. So this is what I had to do. I had to do thermodynamics of reactive metals, electrochemistry of reactive metals, spectroscopy of reactive metals at MIT. And when we say reactive metals, we mean zirconium and hafnium. Why zirconium? Can anybody give me an idea why I'm dealing with zirconium? Because Canada has nuclear reactors producing energy. But Canada is not using enriched uranium and use the natural uranium. So we need to put them in a calandria tube that allows the neutron to go through. And this is zirconium. And since we were buying the zirconium from the US, and the US can always block the supply, we had to develop our own process on zirconium. Then the brother of zirconium is hafnium, which is the opposite. It blocks the neutrons to get in there. So we did all this work. Then when I went to MIT, the interest was magnesium and aluminium and lithium and molybdenum. The last one, molybdenum, people in glass making, they are consuming graphite to produce glass. So they thought that if I can put molybdenum around the graphite, we can save the graphite and still do the glass blowing. The second part of this, it was at that time, General Motors came and they wanted to develop the new magnets. The new magnets was the rare earth magnets. One speaker was referring to the damage that the Chinese made into their environment for getting neodymium, but the Chinese did not invent the magnets. The magnets were invented in General Motors. And that's why they came to me and they say, how much money you want? I said, the money of a professor plus 5,000. They gave it to me. And I worked for 4 years because they wanted me to do this design of molten salts and do the industry scale up. We went from a beaker to 1,000 pound in 2 years. And then calcium also is used in this process to make the neodymium iron boron magnets. After that, there was a brief thing always coming to Greece. I became a professor in Patras. I realized that things have not changed since the time I left. After 3 months, I quit and I went to Dalhousie University, which is in Halifax, Nova Scotia, and I started working with powder metallurgy, surface modification, and coatings, electrolysis plating. All these things you can find presently. The powder metallurgy led to artificial intelligence, how you can make a complicated scheme by using only powder like flour, and you can bake it. The surface modification is something that we can make the surface very indestructible. And we did with aluminum, magnesium, and copper nickel alloys. And then, after that, I started my own laboratory in Dalhousie, and here you have all these things that you read there, came out of my kids playing with something which is called transformers. If anybody remember transformers, and I thought, imagine if you try to make transformers out of metal. It would be all these nice, very movable things would be impossible. Well, the only way to do it is by powder metallurgy, and you can actually do the shapes you want. Then electrolysis plating, it is because of the computer's need. And then corrosion in the marine environment. This has to do with the corrosion of the pipes in military equipment, and the modification of the electric arc furnace design. So those were the things which, after 200 papers, people thought, and this is SIPS is an organization in Canada, that we should have a Kipouros International Symposium, and that happened a year ago in Thailand, in Phuket, Arcadia. So, why we need molten salts? Oops. Because some of the elements in the periodic table, there's no way other than molten salt. So the blue is, you can do it in water, the red is those that you cannot touch water. And that is what brought me into this field. Now, remember that this is supposed to be a conference where mathematics meets chemistry and chemistry meets mathematics. And the objective here is how we are going to have to measure the vapor pressure over a system and coordinate this with the phase diagram. Here is a system. It's a very easy, you would say. It is a binary system, but it's not the normal binary system. The side here is the alkali chloride. Oops. The alkali chloride, even upon melting, gets only a few millimeters of pressure. On the other side, if it is zirconium tetrachloride or any other of these, it doesn't melt. It sublimes, and in order to melt it, you have to put a pressure of 230 atmospheres. So this phase diagram now combines this, which is non-volatile, with this, which is totally volatile. And the phase diagram shows that there is a compound which stabilizes the right part with the left part. So therefore, if we do not use mathematics, people thought, oh, we can try and measure it and we can make electrolysis out of this. Well, here you can see the tools, the mathematical tools are three, is the Gibbs phase rule, which tells you how many parameters you can have. The Gibbs energy, the previous speaker said how much money I can make by taking out of the free energy, but there is an entropy there tells you not too much. And then there is the Gibbs-Helmholtz equation, which tells you that, those things are not straight line. And the capability of this straight line, which affects the system, depends on the system itself. So, in our lab, my professor, my late professor, was, again, a Greek, educated in England, and he thought he knew everything, and we don't need those mathematics here. And here is now the result. The result of the previous years, this fellow and this fellow were from the same department, and you can see the results are only here or there. It makes no sense. Then you have other previous workers, like the Soviet Union workers, who thought that they were dealing with chlorides, but probably they were dealing with oxides. And this is my work after started doing this, because when you measure the vapor pressure of water, you can measure it as you go up, and you should be the same as it goes low. Instead, they said, oh, only this we were interested. No, they were not interested there. They just had a lot of other gases involved there. So we set out to analyze this by various zones. And if I go back for one thing, then you can see in the areas 1, 2, 3, 4, 5, then the degrees of freedom are 1. And then in the other, the degrees of freedom are 2. So you play around with these. They are restricted. You cannot do whatever you think you can do. that no, how do I do it? What's happening here? I want to.
Here.
Okay, well.
Huh?
Okay. So anyway, if you look at the zones, then the compound which forms in the middle decomposes, decomposes into the chloride and the other chloride which is volatile, and they are in equilibrium. Those things, the zone 2, also you can calculate the free energy, and then at equilibrium this is 0, and then you can have that the slope of this phase diagram should be that. And this way, and what is it? Yeah. Okay. And as you go along, you can figure out the slopes of the phase diagram. So what is this now? It is a mathematical manipulation. You have the free energy as it is there, but by doing the mathematics, you figure out the slopes. And not only the slopes, because the slopes determine the phase diagram. So this is what is happening, the pressure versus 1/T, because this is what we are interested. Can I use this system, or what part of this system I can use to make electrolysis and get the metal out of it? So those things and the slopes are shown here. Those help us to develop the true phase diagrams for all these systems. And I did this regardless of my phase or my degree of the PhD degree, which was on electrolysis. I had to do this in order to develop the whole systems. So this is totally different now. Normally when you go as a chemist to do an experiment, you take your compound, you prepare it, and then you try to build up and make this. Here, we develop by mathematics what the shape will look like, and now we have to figure out what and how we are going to purify the zirconium tetrachloride, for example, which does not melt, and collect the clean here. This is a thing that we invented. You put here glass wool, you put tin, solid tin, and then as you raise the temperature, the zirconium tetrachloride bubbles through tin and deposits itself in the cold part of the apparatus. The garbage, whatever garbage is left here. So this now I have a good thing, and I can use in electrolysis, I can make whatever I need to make. If I need to determine the phase diagram to compare with what theoretically I produce, then all what we need to do, put the compound that I form here, I pull a vacuum, I flame seal it, and here I can determine the phase diagram under its own pressure. And under its own pressure, this is something that probably you have not seen in your life, is a Bourdon gauge, which actually you put a compound here, you flame seal it, and then there are 2 pointers, and you have to match the 2 pointers and measure by a manometer, which is here, you measure the vapor pressure. And this is very important because if you do not be careful with that, the vapor pressure is so big that can actually one of the students lost his eyesight because he broke, and so That's why we are very careful. And after you prepare all these things, you can actually prepare for electrolysis by mixing the necessary things. So, how that relates to Ithaca. You remember at the beginning you said you set out to be on a trip, mine trip is coming down, and through the poet of Konstantin Kavafis, you can read this in English, but for those who speak any Greek, it is «Αν φτωχική τη βρεις, η Ιθάκη δεν σε γέλασε, έτσι σοφός που έγινες, με τόση πείρα, κατάλαβες τι σημαίνουν Ιθάκες». That means Ithaca does not fool you. You knew what you were getting into, 50 years of me being out of my country and in China and Japan, but you become so wise after this that you understand what this trip meant to you. So, what happens here? So we have to thank few agencies, the National Agency of Canada, the Atlantic Innovation Fund, General Motors Research, GKN Metals sponsor all my work on powder metallurgy, and I was the director for 15 years of the Minerals Engineering Center. So I did all the analysis free of charge. Oops, what happened? Oh, no, it doesn't finish. Okay? No. And then I have to thank, first of all, some of these guys are my professors. Paul Bishop is my older student. He is a professor now, dealing with the F-35 planes and the companies that make it. George Arjura runs the engineering. Nazila Dadvan, an Iranian student, one of the smartest students that I ever had. She is now the director of Texas Instrument Coatings in California. Paul Berg is the pure lithium Boston startup in MIT. And research students, which are from various nations, and some professors from China, from Libya, from France, and 38 more students. So, and then I have to thank you as well for putting up with my presentation.